Hello, I'm Júlio Frigério, 6th year PhD student, and I would like to show you a quick sample of the talk I will give in the upcoming SEiP Affiliates meeting, Microseismic Monitoring with Deep Learning in the Image Domain. Last year, I showed you a method to image the source of earthquakes and microseismic events. It consists of an adaptation of RTM, and it can be thought of as interferometry in the image domain. Patches of the image obtained with that method are input to a convolutional neural network, which is structured as an encoder followed by a binary classifier. It is trained to detect whether or not the input patch of the image contains an actual source of seismic events. This year, I will show the application of this method to the real DAS data collected during the stimulation phase of the project SEiP in Utah. This project is an enhanced geothermal system operated by Fervo Energy near the Utah Forge geothermal project. The data contain records of DAS fibers placed in 3 wells: the Delano vertical well, one deviated well from the Forge project, and one branch of the Frisco horizontal well used in the stimulation of the geothermal field. Using the records from those DAS fibers, I employ the imaging method to create images of the source of the microseismic events. The images are 3D and present a clear energy concentration at the correct position of the previously catalogued microseismic events. I present 3 examples of events at different locations, and they all show similar characteristics in terms of resolution, signal-to-noise ratio, and shape. Then I show the application of the neural network to patches of these images, and the result I obtain in the event detection procedure. In this experiment, the neural network was successful in accurately predicting the existence of an actual source in the image. I look forward to connecting with you all in the coming SEiP Affiliates meeting. See you!
Hello everyone, this is Rustam from Stanford Exploration Project, and today I would like to discuss some work we have been doing here at SEiP on tackling large-scale inversion problems, focusing specifically on creating an out-of-core vector class and advanced optimization techniques that we have incorporated into our in-house solver. When dealing with massive datasets typical in geophysical inversion, you may ask yourself, how do we efficiently perform basic vector operations when the vectors don't fit into memory? And how do we efficiently manage the associated metadata alongside with the numerical data? Our solution involves an out-of-core approach using Dask data frames that allow for massive, large-scale parallel computations. Think of Dask like a smart scheduler. The client program submits tasks to a scheduler, which then distributes the computational work across multiple workers that process data chunks independently. These workers could be represented by different processes or even different compute nodes on the cluster. This allows us to handle data much larger than available memory. A key concept is delayed execution. Instead of computing everything immediately, operations like calculating data residuals are delayed. We first built a sequence of planned computations. For example, reading data chunks and calculating individual residuals are set up as tasks. And only when we need to reduce these values into one single value, such as get objective function value, the computation actually is performed. This dashboard snapshot shows Dask managing thousands of partition and computing norms across workers, demonstrating the system handling large-scale computations efficiently. Handling large data is one part of the puzzle. The other is incorporating constraints into the inversion, which is crucial for obtaining meaningful results. We explore methods like proximal gradient and ADMM for constraint optimization. A central tool is the proximal operator. You can think of it as a generalization of a projection. It finds a point that balances minimizing a function f and staying close to initial point v. A simple example is when f is an indicator function for a set C, meaning it's 0 inside the set and infinity outside. In this case, the proximal operator simply becomes the standard Euclidean projection onto the set C. For problems minimizing the sum of two functions, f and g, where f is smooth and g might not be smooth, for example a constraint, the proximal gradient method iterates by taking a standard gradient-based step for f and then applying the proximal operator of g to the estimated model. Interestingly, these proximal operators are closely related to a concept of shaping regularization. The proximal operator is equivalent to a shaping operator when the function f is quadratic. However, the framework of a proximal operator is more general. That means that for certain classes of functions g, particularly quadratic ones, we can compute proximal operator by using fast explicit diffusion. A closely related and another powerful technique for constraint problems is the alternating direction method of multipliers, or ADMM. It solves a problem by separating the variable into two variables, x and z, subject to a linear constraint to make them the same at the end of the inversion. ADMM works by iteratively minimizing the augmented Lagrangian with respect to x, then z, and then finally updating a dual variable. Each of the x and z updates can be viewed as applying the proximal operator associated with functions f and g. Let's see this in action with full F4 inversion, or FWI. Here's the true subsurface model we would want to recover. Here's the result of standard FWI without any constraints. That can result into a model that can be quite noisy and lack sharp features. Now we apply proximal gradient method to incorporate total variation, or TV regularization, which promotes blockiness and sharp interfaces. Here's the result of applying a mild TV and increasing the strength of a TV regularization. We can see that with strong TV regularization, we indeed promote blocky nature of the true model, demonstrating the power of constraint optimization.
Hi, everybody. My name is Joe Stiff, and here is the teaser. This is some of the work that I'll be showing at the upcoming meeting in May in Oregon. So I've been working on thinking of a couple of different things here. First, looking at utilizing or even creating synthetic Earth models and utilizing the field velocity model data sets in terms of training and understanding the key importance of that and the overall workflow and the application of neural network-based operators in the context of FWI. And in that fact as well, I've been looking a lot into diffusion networks over some of the work that I've been doing in the summer. And now coming back for this quarter, I've been kind of diving back into this. Not stepping away completely from what I was doing before, but just kind of looking at this as kind of a fun alternative route because my research is over neural network based regularization and preconditioning. So this is was kind of a route that felt very natural. So generally, diffusion or deep learning based diffusion can be seen as both a forward process from coming from kind of a relatively complex distribution to some sort of a uniform Gaussian distribution. But that reverse process is relatively unique. It's hard to kind of accomplish this task. It's not very tractable. And so utilizing something like a UNet might be very important to be able to solve that task and generate something from pure Gaussian noise from this point to this point over here on the right-hand side. And so I've been actually working on the variation of latent diffusion, where essentially you train an autoencoder to essentially decode down some sort of input velocity image. Here you actually just have a clownfish to represent that. But this is going to allow you to essentially do the latent diffusion modeling within the latent space itself, which can bring some potential cost benefits. And so you do everything in the latent space and then decode out using that original trained encoder. And so I've been playing around with creating different synthetics or variations to synthetics. In this case, for a case study for something that might be in the Gulf of Mexico, as you can see with the salt model variation, and the steam model on the right-hand side. Because again, synthetics are important. If you don't get your synthetics right from the get-go, the task at hand is going to kind of go down the drain. And you can see here some of the patch generations that we were able to generate here, moving from the left-hand side over to the right-hand side, from the noisy point to the generated point on the right-hand side here. And then this kind of shows different performances of taking this kind of inline test slice, relatively smoothing it, but then applying this diffusion network and conditioning it for 10 time steps. And you can see from that, 256 by 256 seems to be doing a lot better. And I just kind of got these results very recently. But you can see the differences here are just much more coherent compared to the larger patch size. But sometimes you might want a larger patch size because it does get you quicker towards that kind of conditioning goal. So there's a bit of a trade-off here. So what I hope to get to is essentially working on kind of fine-tuning and understanding the latent diffusion dynamics, applying the model conditioning code to acoustic FWI, just getting into that right now, integrating this inside proximal operators and potentially working on this through STOM, and working on an internal DeVito platform, which we may or may not get to by the time the meeting happens. But that's it, and I hope to see you at the meeting. Bye-bye.
Hello everyone, my name is Haipeng. I'm a third-year PhD student in the group. In the SEiP annual meeting, I'm going to talk about my research on quantitative waveform inversion for groundwater and inject CO2 plume. So as many of you have been aware of that, the time-lapse FWI has been a very powerful imaging and monitoring algorithms because it honors realistic wave propagation and scattering effects. It can provide you the high-resolution elastic parameters. That is why time-lapse FWI has enjoyed very wide applications, either in environmental processes for groundwater monitoring, or for geological CO2 injection, hydraulic fracturing, and of course, oil and gas production. So in the meeting, I'm going to talk about how can we get the cost-effective time-lapse survey using interferometric approach. Also, I'm going to talk about my recent progress on uncertainty quantification using the Bayesian approach for time-lapse FWI. So we're going to talk about how we can perform the daily elastic FWI for groundwater monitoring using the urban dust data. We're going to use the Stanford Dust 2 array to extract the very high quality vertical gathers. So you can perform it on a daily basis, so you can have a almost free daily time-lapse survey. So with the high quality of the daily data, we were able to perform the daily elastic FWI to extract the subsurface changes in terms of the shear velocity changes. And this result shows the FWI on a daily basis more than 2 years, or about 1 kilometer section along the dust array. The result shows a greater consistency with the in situ groundwater measurement, and I'm going to talk about more in details in the meeting. Besides that, I'm going to talk about my recent effort using the Bayesian approach for uncertainty quantification in time-lapse FWI, especially using the Hamiltonian Monte Carlo. The Hamiltonian Monte Carlo is such a method that can be more efficient than conventional Markov chain Monte Carlo because it takes the gradient-informed steps. That is why I believe this can be a very interesting method to pursue for uncertainty quantification in time-lapse FWI. I'm gonna talk about my application to a synthetic but realistic geological carbon sequestration scenario. Um, I'm going to talk about how to estimate the posterior mean and the associated uncertainty. So now with this new method, we are not only able to get the one result but also estimate the uncertainty range using the sparse and noisy time-lapse data for geological carbon sequestration application. Now here is the probability of CO2 plume distribution based on some threshold, and now we can confidently delineate the CO2 distribution, which can be something very important to consider in such a practice. So I'm looking forward to see you all, and stay tuned.
Hi, I'm Thomas Cullison, and I'm a third-year PhD student at SEiP, and my interests cover the intersection of geophysics and seismic and DAS, along with cloud computing, HPC, and machine learning and AI. Some of the previous projects that I've worked on and am still working on, at least in the background, include parallel pipeline or stream processing, DAS data compression using a deep convolutional autoencoder, and DAS channel geolocation. On this last one, you probably haven't seen some of the work that I've done with it, but it is ongoing. As a reminder, with the pipeline and parallel streaming workflows, the idea is within like a Python environment or a notebook environment, can we match something that has like the Linux command line, pipeline processing order, but do it in parallel? For the deep convolutional autoencoder, what we looked at was taking some of the DAS data around the Stanford campus area and seeing if we could compress it beyond the Nyquist. We were able to get about a 30x compression rate, and here I show the original and the decompressed as well as the difference, and also a look at the FK spectrums of both and its difference as well. Regarding the geolocation of DAS channels, a project that I've worked on but is still possibly sitting around in the background for future development, is we have DAS data acquired around San Jose, and there's this loop that you can see down here at the bottom, and the idea is, could we be able to extract anthropogenic noise and use it for using surface waves? Could we use it for some form of FWI in the near surface? And one method I've explored for DAS channel location is related to the method published by Ettore Biondi, where you use a vehicle as a source, it has a GPS in it, and you try to track the vehicle in the DAS data using the GPS to locate the channels, which can be complicated by spooling or deviations in the fiber or cable path. So projects that I have mostly been working on in the past year, and that I'll discuss at this upcoming meeting, includes a first look at the DAS data at the Aquastore geologic carbon capture site. This small software package I call SeisBear. Basically, you use pandas for headers, and doing simulation with the DeVito package. And my focus was elastic, but there were a couple others in the group looking at acoustic as well. So this is an aerial photo of the Aquastore site, and if you look at this kind of blow up here on the right, the red line was the original planned fiber cable entrenchment. It's a little bit shorter than initially planned, and then these circles with yellow and black in them, that's where boreholes are at that the fiber also goes down into, and there are also geophones as well. And here I'm showing a street map-like view of the DAS channels along with the sources. The channels are this snaked row of upside down blue triangles, and the sources are the red stars. And in this map view, I've just overlaid midpoint bends that are at 50 meters to give an idea of what might be a possible area that we could do FWI on. In the next slide, I'll actually show you what some of the DAS data looks like. In particular, I'm going to show you DAS data, 4 seconds of data from the shot shown here for all of the channels recorded. You'll actually see that the channel does loop back on itself. After some pre-processing, This is what the DAS data looks like for that shot. And if I go to the next slide, you will see here we actually have the cable loop back on itself, and these two kind of large vertical streaks here, that's related to slack cable that kind of isn't entrenched, but it does go in some of the boreholes. By comparing the coordinates that were in the SEiP files for the fiber data versus coordinates for the boreholes, this yellow overlaid area is regions that are in some distance close to our borehole. So this is a way to separate out or bin between surface DAS data and borehole data. Using that previous binning, I can pull out the borehole data and just look at the surface data. Moreover, or alternatively, we can also just look at the bore data. You will see that there's some energy down below. The binning isn't perfect, so there may need to be some manual curation of what is and isn't a borehole channel. Using the SEiP package, it was fairly straightforward for me to do header math to pull out a receiver offset gather. And here I'm showing a plot of that. I also wanted to show that there is some, if we're going to use this data for FWI, I think it's important that we find a way to balance the energy between these traces and between different sources and locations. And for your reference, that receiver gather, I'm using the receiver shown here near the center, that is the blue triangle, and all of the sources. For the SEiP package, the reason I was working on this was to have something that was fast and convenient, that was like Seismic Unix or SEPlib or Madagascar that I could work with in Python and Jupyter notebooks. The ideas are the headers are just pandas data frames, so you can add and remove any headers that you want, and you can do header math just using standard pandas operations. I'm also incorporating those map plots that you saw. You can track the file and trace ID, so you only go get the data when you need it, whether that's from disk or memory. Right now I'm just getting it from memory. The data and the headers can be compressed and combined into one file. The idea is to play nice with others, so to integrate with SEgY and to DAS Core and others, and also at some point to get into the parallel, to integrate with the parallel pipeline processing. And this also ties well with some work that Rustam has done using this Parquet compression and parallel processing of his data. To be able to look at surface wave driven FWI using DAS data, we need to be able to simulate elastic waves. And although we do have propagators that have been built by previous students, there are various components that are missing. There can be the free surfaces missing. It could be that it's curtailed to a certain problem and not conducive to reproducibility or future growth and development. So I and several other students have been looking at using DeVito, and here I'm showing some plots of my test wave fields and some tools I built to visualize these 3D wave fields. Thank you for taking the time to watch my elevator pitch here and to listen to the summary of my research. I do hope to see you this coming May. Take care.
Hi everybody, I'm Ivan Dellana, a second year PhD student at SEiP, and today I'm going to do a quick overview on my research on low frequency enhancement and extrapolation using bidirectional LSTM. Why frequency bandwidth extension? So low frequency or high frequency information can help seismic inversion overall. For example, low frequencies are really important to get a good starting model to mitigate cycle skipping, or for example, high frequencies may help in AVO processes. Then overall, we can get an improvement in resolution or in signal to noise ratio. That is also a good byproduct. I'm particularly now constraining the problem to the low frequency estimation. As I mentioned, among other benefits, extending the low frequency band is good for avoiding cycle skipping in FWI, having benefits for very shallow and very deep targets. Then lately in the acquisition side, there's been a large capital investment to get low frequency sources and improving the acquisition, so we get more of this information, being generally really costly. On the other side, in processing, generally we have a really long turnaround time to get this information clean or in a high signal to noise ratio. So I'm proposing a relatively fast bandwidth extension method using machine learning techniques. so we can get the most out of these new acquisition techniques and these processing techniques so we can complement this information. For doing this, I'm building on top of my previous research using long-term memory neural networks that are a kind of architecture specifically designed to handle time series and widely used in speech recognition that have a gate controlling system that allows you to capture long-term and short-term dependencies on our time series. Something interesting of LSTM is that they were the precursors of transformers and attention-based neural network mechanisms, and with the advantage that they don't need that much memory to be implemented, and also it's easier to handle the input data with different dimensions. I'm implementing the proposed methodology as I showed on my previous report, trying to infer low frequency information on two common receiver gathers that were provided by Shell that had an identical geometry, but one was acquired with an ERGAN source and the other one was acquired with a TPS source. We can see here clearly how the TPS common receiver gather has lower frequency information percent, and also we can see that there are some other events that are better defined, particularly for the far offsets. So as an initial test, we just implemented the previously trained neural network without any further refinement to the ERGAN data in order to obtain a low frequency counterpart and then compare this prediction to the TPS information. We can see as it was designed that the prediction honors the phases seen in the ERGAN data, but nevertheless the phase frequency dependencies between the ERGAN and the TPS is more complicated, so further refinement is needed in order to capture these kind of dependencies. So the main scientific question I'm trying to address is how much we can build reliable synthetics to get a TPS-like signature or TPS-like low frequencies starting from ERGAN data, opening a lot of possibilities from the signal processing point of view if we can get such an information only from synthetics. And even further, if we can actually afford TPS sources, how much sources and how much sparse information do we need to better constrain our labels? And that's it. Thank you very much. I'm looking forward to the meeting and seeing everybody soon.
Hi, I'm Sunu Kim, second year PhD at SEiP, and this is my meeting teaser for SEiP Sponsor Meeting 2025. It has been almost 10 years since the first deployment of DASP cable on Stanford campus, because in August 2016, 2.4 kilometers of DAS cable was deployed in a two-dimensional array in existing telecommunication conduits underneath the Stanford University campus. And it's just crazy to me that it's almost been 10 years. And since then, our array has grown to go from Menlo Park all the way in this little rectangle to not everywhere, but almost everywhere on campus. That includes all this faculty housing area that goes through Green Center. And we did recently, I guess earlier this year or last year, did move the interrogator from the Green building to the NVIDIA building. So the suburb has been nicer too, a lot of good changes. But the problem is that the coupling conditions is still pretty complicated because as much as it'd be amazing, I know we can't just deploy the DOS cable like 10 centimeters deep. So we have a lot of layers, and I tried jumping on the manhole to see if my signal can be picked up, and it can be. It's just that I need to jump right on top of it. I just thought the view would be nice and, I don't know, teacher appropriate. But there's been a lot of effort to try to find any meaningful ways to navigate the coupling condition problems, and this was one of the efforts. And I did mention this last SAP meeting, but just as a refresher, we do have an experimental setup data from Nokia Bell Lab where essentially we're interrogating the same fiber in two different directions, and you can see green and blue. There's probably definitely better colors to do this, but yeah, essentially direction A and direction B, and the raw data looks like this. And it's really hard to see what's going on just because the fiber is very long. Like it's not exactly at 50 kilometers, but it is definitely 40 something. But when we zoom in to somewhere closer so we can see, you can see that there's a pretty large spatial lag, which means that we need to correct for this before we can do anything about it. Kind of looking like this. Yeah, just slide it in. And using some simple correlations, I can correct for this spatial lag, and now the data is going to be more usable. And what I was, yeah, so now it is A and B, and you can see that, oh, like it's about the same data, same events, but it does have slightly different signal to noise ratio. It is a little noisier on the B, a bit more current on the A, and by stacking, I could get some more coherent data with the signal to noise ratio a little more improved. But I thought what's gonna be actually fun is essentially combining DAS and DSS system in the same setup, in the same interrogator, Bible, everything. So essentially by using the time shift between the two directions, I can I can just use that. So now it is dual mode sensing where DAS being dynamic acoustic signals and DSS measuring static or quasi-static strain changes can take advantage at the same time. And I think I should think more about the applications, and there's still time until the actual presentation happens in May, mid-May, I think May 19th. So I'll see you soon next month at SEiP it's not Tahoe, but whatever result it is, it's gonna be nice. I'll see you in a month and a half.
Hi everyone, I'm Cewen Liu, a postdoc in the SEiP group. It has been about half a year since I joined the SEiP group, and I'm excited to share some of the progress I have made in my research on time-lapse full waveform inversion, which I will be presenting at the upcoming SEiP Affiliate meeting. Over the past few months, I have been working extensively with DeVito, which is a symbolic, high-performance computational framework. DeVito allows for rapid prototyping of wave equation-based solvers while ensuring computational efficiency by automatically generating highly optimized stencil code. Using this powerful tool, I have built up my understanding and implementation of several advanced inversion techniques. Based on DeVito, I have built up my understanding and implementation of several advanced inversion techniques. Specifically, during this period, I have successfully implemented standard full waveform inversion, multi-scale full waveform inversion, multi-parameter full waveform inversion, and most importantly, time-lapse full waveform inversion, which is my main focus. Here, I'm going to talk about the progress of my time-lapse full waveform inversion research. So, what is time-lapse full waveform inversion? Time-lapse full waveform inversion, also known as 4D FWI, is an advanced seismic imaging technique that uses seismic data from multiple time points to build high-resolution subsurface models. Typically, we work with a baseline survey and a monitor survey. One key advantage of 4D FWI is its ability to use both amplitude and phase information of seismic waves, which help us better understand complex reservoirs and monitor things like carbon plume migration. Importantly, 4D FWI is very sensitive to small changes in the subsurface, which makes it powerful for monitoring subtle movements underground. However, it also comes with challenges for the time-lapse technique. For example, it requires multiple datasets and many iterations, making it computationally expensive. Also, it heavily depends on high-quality, consistent seismic data. The biggest challenge for the time-lapse FWI may come from the 4D signals are often very weak and sensitive to noise, which makes the detection tricky. As you can see for the Malmosy model, the velocity changes tend to be small. Here is relatively 1%, which makes the time-lapse signal very weak compared to the baseline and monitor signals. With these challenges in mind, we have implemented and tested several different time-lapse FWI approaches using the DeVito framework. So let's review some typical 4D FWI workflows. For the simple parallel inversion, we invert baseline and monitor models separately using a smooth initial model. then subtract the results to get time-lapse changes. As for the sequential inversion, we first invert the baseline model and then use it as the starting model for the monitor inversion. The central difference method involves two stages. The first stage is the forward inversion of baseline and monitor model. The second stage, we set the first stage inversion model as the initial model and implement the cross inversion as shown in the figure and compute the central difference. For the double difference method, we involve the double difference loss function displayed in the formula, which is sensitive to the subtle 4D changes. As for the joint inversion, we add a regularization term for the baseline and monitor model difference, helping to keep both models updating consistently. For my experiments, I used the SEiP model, which is more realistic for 4D applications. The setup includes 10 shots and 201 VSP receivers from 100 meters to 1400 meters depth. As shown here, the 4D data changes are subtle relative to the baseline and monitor datasets. We test different 4D inversion methods for the SEiP model. We can see that the double difference performs well, which can capture the carbon plume shape accurately. The central difference and the joint inversion methods can produce cleaner results with reduced artifacts. I also test a shallower receiver setup from 100 to 1000 meters depth. As expected, the results were slightly worse due to less coverage. But the double difference methods still perform well. Interesting, a joint and the central difference methods remained promising. Then I combined surface and VSP receivers to mimic more realistic field conditions. We add 101 subsurface receivers spacing from 100 meters to 2800 meters. Here it seems that the joint inversion methods show better robustness than the other methods. We also tried sparse receivers layouts with 11 subsurface receivers plus VSP configurations. Compared with the result with more subsurface receivers, the inversion result looks much more cleaner. It demonstrates that the 4D FWI doesn't require subsurface dense receiver coverage, since adding more subsurface receivers increases the amount of data to fit. It can actually make the FWI convergence more challenging. Besides, we have involved noise tests for 4D methods, both the Gaussian noise and the uniform noise. For the Gaussian noise, here I show the result with 30 dB Gaussian noise adding to the baseline data and 10 dB noise adding to the monitor data. We can see that the inversion result has no obvious changes relative to the result without Gaussian noise. Since our 4D FWI method focuses on minimizing the L2 norm of the data misfit, the zero mean Gaussian noise has more impact for our final inversion results. In contrast, uniform noise may have a wider amplitude range and less predictive distribution. Here, we also test the uniform noise. We add 10 dB uniform noise for both the baseline and monitor datasets. The noise level is strong so that we can observe the baseline and monitor data are strongly affected. It is very hard to identify the valid data changes from the noisy dataset. It can observe that the parallel difference result is very noisy. The double difference method and the joint difference method are still very robust for the uniform noise, even with 10 dB strong level uniform noise. In addition, I have also explored 4D multi-parameter time-lapse FWI. I'm also planning to investigate near-surface changes using our 4D FWI methods, including both subsurface variations and seasonal effects. Looking ahead, I plan to explore elastic 4D FWI within the DeVito framework and apply it to both the SEiP model and Outway datasets. Besides, I'm interested in combining 4D FWI with deep learning techniques to enhance both accuracy and efficiency. Moreover, I'm also interested in 4D FWI combined with seismic imaging topic. I'm very happy to discuss any of these research directions with you during the afternoon meeting if you are interested. Looking forward to seeing you in May. Thanks.
Hey everybody, my name is Hamad. I'm a first-year master's student and I hold a bachelor degree in geophysics from the University of Leeds. And before joining Stanford, I spent 5 years working as an imaging geophysicist at Aramco. Today, I'm excited to share a quick overview of my current research on seismic low frequency extrapolation via physics-aware conditional diffusion models. This is a review of what I'll be sharing in the upcoming SEiP meeting. Our focus is on improving seismic imaging by addressing one of the long-standing challenges, which is the lack of low-frequency data in the field recordings. Low frequencies plays a key role in full waveform inversion, especially for recovering the low wave number components of the subsurface model. Without them, we risk falling into local minima, also known as cycle skipping, which compromises the inversion results. To address this, we leverage the power of diffusion models, which is a recent class of generative models known for their strong performance in tasks like image synthesis and embedding. These models learn to denoise data gradually, allowing us to generate samples from complex data distributions. But we don't stop there. We use conditional diffusion models, guiding the generation process using the available high-frequency data. This conditioning helps ensure that the extrapolated low frequency are consistent with the observed data. To achieve this, we propose to incorporate physics-based constraints into the sampling process, such as enforcing kinematics consistency or leveraging local plane wave priors. This physics awareness will help us generate more plausible and physically consistent extrapolations. To wrap up, I would like to leave you with a couple of thoughts that we are currently exploring. First, we are interested in understanding how much physics guidance can enhance extrapolation, especially when dealing with out-of-distribution data. This is critical for generalization to real-world seismic data. Second, we are asking whether physics-informed sampling techniques such as guided DDIM can make the generation process more efficient without sacrificing the quality. These are exciting directions, and I'm really looking forward to discussing them with you during the meeting. That's it, and thanks for listening. I'm looking forward to seeing you soon.